Okay, so in the last lecture, we talked about how to represent sentences from English into predicate logic. And that shows us that predicate logic has some additional structure that propositional logic didn't have. In particular, predicate logic has the structure to represent the inner bits of sentences that are important for logical inferences. So in particular, names, the role of names in sentences, the role of predicates in sentences, and it also has the ability to represent quantifier phrases and the way that quantifier phrases like all or some connect into other things inside the sentences. And that's why we needed the device of variables, because variables allow us to connect the beginning phrase, everything or all, with subsequent references back to it. Okay, so this is logic though. So what we want now is we want to be able to use to represent correct inferences that use these new things. Now, just like in propositional logic, every special logical word we identified came with inferences, came with a kind of inference that you would be permitted to make because of the way that word works. Now we're going to see that predicate logic is very much the same. In particular, the predicate phrases all and some also license certain inferences. Today we'll focus on using the universal quantifier. And as with our propositional words, there will be two rules. There will be an elimination rule, that is how you reason from universally quantified sentences. And there will be an introduction rule, that is how do you reason to universally quantified sentences. Universal elimination, the rule we'll talk about in this lecture, is the easier of the two rules, and that is because universal sentences are very strong. If I say everything is F, that gives me lots of information. If I know that everything is F, then I know that Alice is F, and Una is F, and Roman is F, and it goes on and on. Everything is F. That's an incredibly powerful thing. So universal elimination is basically the ability to use universal claims like that, and then drawing the inference that a specific thing has the feature. So universal elimination is just that. It's the rule that says from for all x, phi x, you can infer phi a for any name whatsoever. Okay, and it is one of these rules that just gathers dependency numbers. So if you have on a line for all x, phi x, then on any subsequent line, you can write phi a for any name a, and you carry down the dependencies from the for all x, phi x sentence, the line it was on. Okay, now we'll see in just a second, I'll show you examples of this rule in use. However, it's important to start with a couple warnings. So the first warning is this rule, universal elimination, is only applicable if the entire sentence on the line is a universally quantified sentence. So that means the universal quantifier better come first, and then everything it applies to will exhaust the rest of the sentence on the line. That is not true of the sentence you see right here on the slide. So the sentence on the slide, the for all x, in this case, the for all x applies only to the fx. It doesn't apply to the g. It doesn't apply to the ga there. So this is different. Let me just be clear. The sentence that goes like this, for all x, fx, arrow ga, this sentence is a universal sentence. This sentence over here, not a universal sentence. Okay, so you cannot, let me write this in red just to be absolutely clear, you cannot infer for all x, f, a, arrow, ga, sorry, that wasn't even what I meant to say. You can't infer something like fa, arrow, ga from that sentence because it's not a universal sentence. It's not of the form for all x, phi x. This sentence, for all x, fx, if for all x, fx, then ga, is actually a if-then sentence, a conditional sentence. It says if for all x, fx, then ga. So its main connective is if-then. it's not a universal sentence. So you can't apply universal elimination to a sentence unless it's a universal sentence. Okay, second caution. The second caution is the only legitimate use of universal elimination is where you take off the quantifier and then the corresponding variable, you replace it everywhere it occurs with the same name. So you can't replace different occurrences of the variable with different names. And also you'd better replace every occurrence of the variable with a name, or what you end up with is not a sentence. So for example, you cannot from this infer FA arrow GB because that puts in different names in the two places. That's not allowed. You also cannot infer, say, FA arrow GX where you didn't replace the second X with the name A because, again, that's not a sentence. So for all X, something, that thing, you have to replace all the occurrences of the variable X with the same name. That's how universal elimination works. Okay, so now on to some examples. And we'll start actually with an argument written out in English. All Frisians, so if you don't know, Friesland is part of what's now called the Netherlands. Friesland is a little tiny part of that to the east of Amsterdam. So this is your geography lesson of the day for those of you who didn't know. Again, I chose it though in this case because it starts with F. So all Frisians are gregarious. Alvin is a Frisian, therefore Alvin is gregarious. Okay, so let me first just symbolize those. So all Frisians are gregarious. We could say that is for all X, if X is a Frisian, then X is gregarious. Alvin is a Frisian, so AF, and in the conclusion, Alvin is gregarious, AG. Okay, notice again how I'm saying it backwards from the way I'm writing it, because in English, we prefer to say the name and then the predicate. So I say AF, although it written down it's F, then A. Okay, so let's prove this good old-fashioned proof style that we did already in the first half of the semester, now using our rule, universal elimination. Okay, so for all X, Fx arrow Gx is my assumption. My other assumption is Fa. And what I want to prove is Ga. Okay, so here's how I'm going to do it. Is I know that A is an F. I know that anything that is F is G. So that is true of anything I want to pick, but that's up to me to pick something. Universal elimination doesn't tell me which name to choose. That's up to me. And so I need to think, what will it be useful to know has this feature that if it's F, then it's G? Well, in this case, there's only one person in play, Alvin. So I'm going to say it for Alvin. Okay, so I'm going to infer on line 3. If Alvin is Frisian, then Alvin is gregarious. So that comes from line 1. This is my first application of universal elimination on line 1. Okay, if FA, then GA. And now we're just back with lines 2 and 3. We're back in the safe territory of propositional logic. Okay, so from these two, I can now just infer GA. So 1, 2. This from 3 to modus ponens. Okay. Okay, so let's prove this this example on this page. Okay, our premise here is for all X, for all Y, Fx and Gy. Conclusion is Fa and Gb. That first sentence is the first sentence there is a little bit confusing to parse what it says, possibly. It says, for anything that's X and for anything that's Y, Fx and Gy. Basically in English, it says something like for any two things, the first of those two things is F and the second is G. Okay, so let's just write this down. Our premise for all X, for all Y, Fx and Gy. Okay, now what can we do with this first sentence? This first sentence is a universal sentence. It's first, as you go from left to right, the first thing you run into is for all X, and that for all X applies to everything that comes after it. So in this case, what's in the green box here after for all x applies to that. So this is like phi x. So what universal elimination tells me is that I can take off the for all x, I can put in whatever I want for the x. In this case, the x lies under f. So I change this first line to for all y, fa and gy. So notice that y doesn't get touched. The y is connected to the for all y. When I take off the first quantifier for all x, I just replace x with the name. Okay, so that follows from 1, universal elimination. And now 2 is also a universal statement for all y such and such. So I can take that off. I can put in whatever name I want for y. In this case, I want b. So I now go to fa and gb. So again, now 2 universal elimination. Okay. So there we go. For all x and for all y, fx and gy implies fa and gb. Okay, this next proof on the next page is just like the one on the previous page, except instead of getting gb, now I have ga. And the whole reason for writing this down is to remind you that universal elimination is no restriction on it. In other words, you can put in whatever name you want when you take off a universal quantifier. So I can put in the same name I used before if I want. So that's what I'll do in this case. So again, my assumption for all x, for all y, fx and gy. My assumption, just like last time, I'll start by taking off the universal x quantifier. So I'll take off the for all x. I'll replace x with a, fa, and gy. So that's from 1, universal elimination. And then now I'm going to take off the y, but this time, unlike last time, I'm going to put in I'm going to put in a for y. So fa and ga from 2, universal elimination. Okay, so again, a reminder that universal elimination doesn't tell you what name to put in. It tells you can put in whatever name you want, whatever name will be useful to you. Okay, so now let's do an example of a proof where the overall structure doesn't obviously lend itself to universal elimination. So it's not like in this case, our premise is a universal sentence. Our premise is a conditional. So this is a prime case. This first sentence, this is a conditional. It's an if-then sentence. It's not a universally quantified sentence, so it is not a sentence to which one can apply universal elimination. Okay, so let's starting with our premise. If P, then for all x, fx. That's our assumption. Okay, now the conclusion I want is if P, then fa. Please, please resist the temptation to try to turn line 1 directly into the conclusion, if P, then fa, citing universal elimination, because universal elimination does not apply to line 1. Line 1 is a conditional, not a universal sentence. However, the conclusion is also a conditional. So thinking strategically, I think, why don't I assume the antecedent of the conditional and prove it's consequent? So I assume P. This is now my strategy for proving this, because I know once I assume P, if I get FA, then I can do conditional proof and I'll be finished. Okay, so in this case, once I assume P, then I can break the premise on line 1. I can take off the universal for all x fx. So 1 and 2 modus ponens gives me that. And now I can get my FA from line 3, universal elimination. Okay, and that's what was wanted. So now I get if P, then FA, and now I've conditionalized on the assumption of P in line 2. So I get to take that out. So it depends just on 1. So that's 2 to 4 conditional proof. Okay. Okay, one last proof in this session. I'm going to prove now that it's not true that everything is F from the fact that A is not F, which of course, if you think about it, is kind of an obvious fact. If A is not an F, then it can't be that everything is an F. So let's think this through as we're writing down the premise. So A is not F. Okay. How do I get that conclusion? Okay, not everything is F. Well, now remember, we still have all the propositional logic rules available to us. So in particular, we have reductio ad absurdum. So now if I assume for all x fx and I get a contradiction, I'll be able to assert not for all x fx. So on line 2, I'm making a strategic assumption, thinking that soon I'll do reductio ad absurdum. Okay, in this case, it will be very soon because line 2 is universal. It means I can now get F applied to anything I want. Now, again, it's not going to tell me, line 2 doesn't tell me which thing to apply it to. That's up to me to think about what I'm trying to do. I'm trying to get a contradiction with line 1. Line 1 says not F, A is not F. Now I'm going to say A is F because line 2 says everything is F. So now I say A is F. That follows from 2, universal elimination. And now I have my contradiction, A is F, A is not F, so 3 and 1, and introduction. Okay, so that leads to the negation of the thing I assumed on line 2, so 2 to 4, reductio ad absurdum, and that kicks out the assumption of line 2, so I'm back now just depending on 1. So it does follow that if A is not F, then it's not true that everything is F. Okay, so these were some basic proofs using universal elimination. Universal elimination is a straightforward rule that has a couple points at which you need to be cautious. You do need to be cautious that you only apply it to a sentence that really is a universal sentence. That is a sentence that begins with a quantifier, and that quantifier applies to everything else on the line. Okay, so universal elimination doesn't apply to conditionals, doesn't apply to conjunctions, it only applies to universal sentences. The other thing to keep in mind is when you take off the quantifier, you must replace that variable at all places it occurs with the same name. With those two restrictions in mind, it's an incredibly powerful rule. You can insert any name you want. Then the question is, what will it be useful for you to know? Okay, so we'll continue next session with some more inference rules applied to, or the next inference rule for universal quantifying, that is universal introduction.